Every time you paste a URL into Chrome, before you even hit enter, Chrome already knows if that site is dangerous. No internet needed, just a local structure making the call in microseconds. Chrome has a list of millions of malicious websites and needs to check every URL you visit against it. But hitting Google's servers every single time would be unbearably slow. So instead, it uses a Bloom filter, a probabilistic data structure that doesn't actually store the list, but just tracks the fingerprint of it using a bit array, which is just a row of zeros and ones, where a 0 means definitely not here, and a 1 means probably here. Here's how it works. Say you want to add the word pen to your filter. Instead of storing the string, you run it through a few hash functions, where each one points to a position in your bit array and flips that bit from 0 to 1. You do the same for apple and pineapple, and if a bit's already flipped, you just leave it. So the filter now holds the fingerprint of all 3 words, with no actual string stored, just patterns of ones. Now someone queries banana, you hash it, check the positions, and hit a 0, which means mathematical certainty that banana was never added, so you reject it instantly without touching the database at all. But then someone queries pen pineapple apple pen, a string you never actually added, but every bit it needs happens to already be flipped from earlier insertions. So the filter says probably yes. That's a false positive. The filter got fooled by coincidence, so now you go check the actual database to confirm. A data structure that can lie sounds like a bad idea, but it only lies in one direction, because it will never tell you something is missing when it's actually there. It might occasionally say something is there when it isn't, but that just costs you one extra database call. While every true negative gets rejected instantly at O of 1 with no database, no network, nothing involved. So when you visit a site, Chrome checks the Bloom filter first. And if it says no, you're through instantly. And only if it says, maybe does it actually make the network call to verify, which means billions of requests that never needed to happen. Just don't. If you made it past kindergarten, you know the standard 7. Arrays, linked lists, hash tables, stacks, queues, graphs, and trees. The bread and butter of CS 101. An array is a row of cubbies. A linked list is a treasure hunt. A hash table is a labeled locker. Clean, logical, satisfying? For a while, I thought the hash map was peak engineering. The ultimate cheat code that turned my nested for-loop nightmares into O of 1 enlightenment. But in production, elegant logic is a luxury you can't really build to the server. When your system is handling millions of requests, those clean textbook structures don't just slow down, they break. They're too hungry for RAM, too slow for modern drives, too well behaved for a world that's actively trying to set your server on fire. So engineers started cheating, but in smarter ways. The structures actually keeping the internet alive aren't elegant. They're aggressive and counterintuitive, and the kind of thing that makes a CS professor uncomfortable. Here's what scale actually looks like. The Bloom filter only answers one question. Does this exist? What happens when you need to know how many times something exists? That's a different problem, and it needs a different approach. Every second, millions of people are watching, skipping, and replaying videos, and YouTube needs to know in near real time how many views each video has. The obvious solution is a giant hash map, with every video ID mapped to a counter. Simple, clean, and completely impossible at YouTube's scale, because storing exact counts would eat more RAM than they can afford. So YouTube doesn't store exact counts, it stores good enough counts. This is the count min sketch, multiple rows each with its own hash function. When a view comes in, you run the video ID through each hash function. Each one points to a position in its row, and you increment every one of those counters every single time. This is happening constantly across hundreds of millions of videos. To query how many views a video has, you use the same hash functions and same positions and take the minimum value across all rows. That minimum is your answer. Not exact, but provably close. 2 different videos can hash to the same cell in the same row, and their counts bleed into each other, which is called overcounting. It only inflates numbers and never deflates them. So you take the minimum, the row least contaminated by collisions, because the true count is always at or below what you're seeing. Tiny memory footprint, billions of events per second. YouTube doesn't know exactly how many times you watched that video at 3 a.m. It just knows approximately. And at that scale, approximately is genuinely good enough. Textbooks say, when 2 keys collide in a hash map, you just chain them in a list, which is polite and orderly and completely useless when you need deterministic speed. Cuckoo hashing gives every key 2 possible homes, one in each table, a primary spot, and a backup. Under normal conditions, lookup is instant, because you check both at the same time, and you're done. When a key arrives and its slot is empty, it just moves in, straightforward. But when a new key arrives and its slot is taken, it doesn't wait around. It kicks whoever's there out. That evicted key goes to its backup slot and kicks that one out too, and the chain keeps going until everyone settles. Sometimes the chain loops back to where it started and nobody can settle. When that happens, the whole table rehashes with new hash functions and everything gets reinserted from scratch. It's rare, and the trade-off is worth it. Once everything settles, every key is in exactly one of 2 places, and that's the whole guarantee. You don't search through anything, you just check 2 spots at the same time in hardware, and you're done. Not average case fast, worst case fast, which is what actually matters when you're forwarding millions of packets per second on a high-speed network router. Every time you write to a traditional database, the disk has to physically seek to the right location, and that takes around 4 milliseconds, which sounds tiny until you've got thousands of writes per second all queuing up, and the disk just becomes the thing everything is waiting on. Discord processes 4 billion writes every single day, and at that scale, a traditional disk-based database doesn't just get slow, it falls apart completely, and you need a fundamentally different approach to writing data. That's where the LSM tree comes in. Instead of writing directly to disk, every write goes into an in-memory buffer called the mem table, which is fast because it's pure RAM with no disk seeks involved. The mem table keeps everything sorted as it arrives, but RAM is limited, so once it fills up, it needs somewhere permanent to go. When the mem table fills up, it freezes, becomes immutable, and gets flushed to disk as an SS table, which stands for sorted string table, where every key is already in sorted order. A fresh mem table starts up immediately, so writes keep going without any interruption. Over time, SS tables pile up, and that's where compaction comes in, a background process that merges SS tables together. Same key in 2 tables. Newer version wins, and the old one gets discarded, leaving cleaner, more compact files organized into levels, all while writes keep coming in. Reading is the honest trade-off. To find a key, you check the mem table first, since that's where the freshest data is. And if it's not there, you go through SS tables, from newest to oldest. Bloom filters and sparse indexes keep this reasonably fast in practice, and the key always gets found eventually. And this is the full picture. The mem table absorbing writes at memory speed on the left, while compaction quietly merges SS tables on the right, both running at the same time. 4 billion writes a day, and the system keeps going without interruption. That's the LSM tree. The whole idea is you never update in place, you never do random disk seeks, you just keep appending and let the background process handle cleanup. It's what Cassandra, RocksDB, and LevelDB are all built on. But what happens when one machine isn't enough? Every structure we've covered so far assumes one thing, that all your data lives on a single machine. One table, one disk, one box. But what happens when the dataset gets so big that one machine physically can't hold it? The obvious answer everyone reaches for is modulo. You hash the key, take the result, modulo the number of servers, and that number tells you where the key lives. With 3 servers, it works fine. Keys spread out, and everything runs smoothly. Then you need to add a 4th server. The formula changes from modulo 3 to modulo 4, and almost every single key remaps to a different server. Every one of those remapped keys is now a cache miss, going straight to the database and at scale. That's not just a slowdown. That's everything falling over at once. So you need something smarter. That smarter thing is the hash ring. Instead of a flat modulo formula, you take your entire hash space and wrap it into a circle. A ring that goes from 0 all the way around back to 0. And the one rule is that you always move clockwise. You hash each server, and wherever it lands on the ring, that's its spot. Server A here, server B here, server C here, just points sitting on a circle. When a key comes in, you hash it, find where it lands, walk clockwise until you hit a server, and that server owns the key. That's the whole lookup. No formula to break, no modulo to recalculate. When server D joins, it drops in between 2 existing servers, and only the keys in that new stretch of the ring move over. Just 1 key out of 4 in our example, whereas with modulo, every single key would have moved. When a server crashes, its keys flow clockwise to the next server on the ring, and only that server's keys move, everyone else stays completely untouched. One catch is that with just a few servers, the gaps between them are rarely even, so one server can end up responsible for way more keys than the others. The fix is virtual nodes, where instead of placing each server once on the ring, you place it multiple times at different positions spread around. Load balances out naturally, regardless of where servers physically ended up. This is what Amazon DynamoDB runs on, Cassandra too, CDNs, load balancers, all of it. Thousands of real nodes, millions of virtual positions, billions of keys all finding their home. You add a server, and almost nothing moves. You lose a server, and almost nothing moves. The ring just absorbs it and keeps going. HyperLogLog is about counting billions of things while keeping almost nothing in memory. Twitter tracks unique impressions on every single tweet. The textbook solution is a hash set, where you add each user ID. Duplicates get ignored, and the size gives you your unique count. Clean, exact, and completely impossible at scale, because 500 million tweets a day, each potentially seen by millions of unique users, would need more memory than physically exists if you gave every tweet its own hash set. HyperLogLog takes a completely different approach. It hashes each user ID into a binary string, looks at how many zeros appear at the start of that string, and throws everything else away, reducing the entire input to a single number. The intuition is that each bit of a hash is random, so 1 leading 0 happens half the time, 2 in a row happens 1 in 4 times, 3 in a row 1 in 8, and so on exponentially. If the longest run of leading zeros you've seen is k, that's a statistical signal that you've processed roughly 2 to the k unique items, because more unique inputs means more chances for a rare long run of zeros to show up. HyperLogLog keeps one register storing the maximum leading zeros seen so far. and each new input gets hashed, you count the leading zeros and update the register only if it beats the current record. But a single register is way too noisy because one unlucky hash early on throws your estimate way off with around 30% variance, which is unusable in production. The fix is splitting the work across many registers, where the first few bits of each hash decide which register gets updated, and the remaining bits count leading zeros for that register. To get a final estimate, you use a corrected harmonic mean, a formula built specifically to resist outliers. Real production systems like Redis and BigQuery use 16,000 registers, which is still only 12 kilobytes of memory, and they get under 1% error rates. A hash set tracking 1 billion unique users takes 4 gigabytes of RAM. HyperLogLog does the same job accurate to within 1% in just 12 kilobytes, which is around 330,000 times less memory. That impression count under every tweet is not an exact number, it's a HyperLogLog estimate running on barely any memory across 500 million tweets every single day. We're taught that exact is always better, but HyperLogLog shows that at scale, knowing when exact doesn't matter is actually the smarter call.